So before I start off, we are going to take a step back into traditional machine learning with NLP context, just to, refresh and go back so that you can try and soak in a little bit on stuff that even Kendall spoke about. So one of the things that I'm going to talk about here is, of course, sarcasm detection. And it's a hard problem for natural language, of course, because language is complex as it is, and detecting tricky things like sarcasm is even more complex, as you can imagine. So before I go into that, I want to stress the importance of how important it is to have a good data set. So if you have a data set which you can rely on, your training algorithms or your deep learning stuff is going to work really well. So typically when you have data sets that where multiple people are trying to rate something, right? For example, you have 10 patients and a bunch of psychiatrists are trying to diagnose those 10 patients, and they come up with this diagnosis. I think it's important, how reliable is that diagnostic, right? And how can you rely that all of these people, how good is their level of agreement? And if they randomly diagnose these patients, how good would that be? So there are statistical measures to do that. One of the things that I did, I'm just sharing stuff that I did as an assignment as part of my applied NLP course in my master's when I did it. And one of the things that my professors insisted was to look at this Kappa statistic, right? So this Kappa statistic is something that will help you find out that if 5 people are looking at a tweet and trying to figure out if this tweet is sarcastic or not, these are 5 people who have a certain context in their heads, and they want to see like, oh, is this a sarcastic tweet or not? And then they are rating it. How good is the agreement between these raters, right? And if the agreement is really good, then it's a good enough, they fairly agree that this tweet is sarcastic. So it's a good data set. So I just want to walk through that exercise. It's a pretty simple one. So here I have this notebook called Flays Kappa. So that is our technique. This technique is called the Flays Kappa statistic, right? So before I go through this notebook, let me show you my data set. The data set that I took was downloaded from Kaggle. And this is from The Onion, which is pretty much all the time, publishing spoof news. And they're linking back to some articles. And they have, if you look at the data set, it's a JSON document with article link and the headline. And don't get too absorbed in the headlines, because some of it might be sarcastic and some of it might be like, I don't agree with this, but that's the kind of headlines that we have. And for example, this CEO will send your kids to school if you work for his company. I mean, sarcastic is 0. So let's look at a good one, a good sarcastic example. If you see giant Altoid heading towards Earth or something. So this is my data set. And what I'm going to do is, I have this is like 26,000 lines of these articles. So I have these people, instead of finding 3 people who will sit and say, hey, I find this sarcastic, or I didn't find this sarcastic, I wrote a Python script which will auto-generate my ratings for me. So just to make it easier. And that script is out here. So you can play around with that too. So this is the parsed data set. So you run this against this CSV and you get this rated data set. So the rated data set is having my sentence, just my sentence. And what did rater 1 feel about this sentence? Did they feel it's sarcastic or not? there is a no, there is a yes. So there are 3 raters rating 26,000 sentences, and each one has something to say about it. Each one either says yes or no. Yes means it's sarcastic, no means it's not. So that's what I generated. And then I'm going to now talk about Fleiss Kappa. So Fleiss Kappa, right? So here are some introductory notes. So if you read this, like, it's very statistical definition, but one of my goals in this 1 hour is to make it a little intuitive. So expressing the extent of observed agreement, right? So let me show you an example, a simple example, so that when you expand it to multiple people, you will understand how this agreement is done. So I'm just gonna insert a new cell just to demonstrate this example. Let us say I have rater 1, right, who's rated 100 patients for a specific disease or something, and he found 60 patients positive and let's say 10 patients negative. And there's rater 2 who found 15, so this is positive, so 15 patients negative, and yeah, so this is rater 2 and rater 1. So generally if you see, this is, okay, this is, let me put this table properly. So this is plus, minus for rater 1. And for rater 2, this is plus and minus, right? So now, how many people agreed, what's the level of agreement that this disease is positive, is 60 plus 15 by 100, which is a 75% agreement. This is your observed level of agreement, right? So Kappa says, this is the observed level of agreement between 2 raters, right? And Kappa says, so the Kappa calls this Kappa, when I say Kappa, it's like a measure, okay? So it calls it observed level of agreement is 75%. But my expected level of agreement is what if these people just randomly rated this, right? So I will combine all the positives together, which is 70 by 100 multiplied by all the positives, right, of one rater, which is 30. If you look at 15 plus 15, 30. So this is when they do it randomly. And then I combine this with all the columns, 60 into 15 plus 10 into 15. I'm just trying to demonstrate Kappa here. Sorry, 60 plus 15 multiplied by 10 plus 15. And approximately, if you calculate this, it comes to about, a certain 65.6 or something. And the Kappa definition is, from the observed level of agreement, I subtract the expected level of agreement and then normalize it across like a probability, right? So 1 minus expected out of agreement. And then whatever value you get is in a range between 0 to 1, right? And that value will tell you whether these people have agreed properly or not. If you have 0, that means these raters don't have proper agreement among each other, and you got to go back and inspect this data set and talk to the raters. People generally, companies, they go to companies like Mechanical Turks and all of these people, and they kind of try and give these sentences and say like, hey, rate this for me. And there's people like looking at it and just rating sentences. And you don't know, you want to find out like, how much of these domain knowledge did they have and stuff like that. So just to validate it's a good data set. So this is Kappa example with just, 2 raters. So this is Fleiss Kappa is specifically a technique when you have more than 2 raters. You have 10 people rating something, then how do you calculate Kappa? They made it really easy for everybody. So that's pretty much the formula here. So there's a worked example, which pretty much does the same thing, and it's pretty explanatory if you see. There are 3 raters. They assign 5 subjects to 2 categories. In our case, since you're talking about sarcasm detection, let's say there are 5 tweets. 3 people are sitting and trying to find out this is sarcastic or not. And if you see, it's the same thing that I mentioned. It's just that Flace Kappa has got a little bit of a different formula. So basically, if you see 3 square plus 0 square minus 5, which is the expected level of agreement, divided expected total number of raters divided by this. So this is just a little bit of math, statistics that you might want to go back and check. It all boils down to, hey, what's the mean, and what's the mean number of agreements? And there's a whole bunch of statistical calculations. That's pretty much it. But if you finally calculate kappa, in this particular example, if you see 3 people agree to yes, all 3 are in agreement for the first tweet, right? For the second tweet, 1 is not in agreement. For the third tweet, they are not, there's 1 person who's not agreeing. And for across 5 tweets, there are 3 examples where they are not clearly in great agreement. And if you see, there's a kappa value of negative, which is like, it's not great agreement. Like these people haven't greatly agreed with each other. So, and the sample size is just 5. So let's expand this sample set to 26,000. That's what we've done here. We've taken this data set, which is your dataset.json, which has got all of these entries, and we have, this is the interpretation for kappa. Before I get into that, so this is, poor agreement, slight agreement, So many companies, they actually, when they actually outsource these data set to people and they try to get an agreement, they would want a substantial agreement, not like almost perfect, but at least they would expect the raters to agree substantially. Then it's a good data set for their machine learning model, right? So this is the Flace Kappa, whatever I explained to you, this is the Python code for it. So if you see proportion of all assignments to yes, proportion of all assignments to no, and then it just opens the CSV file, and then it kind of starts reading it. Tweet, I call it tweet, but headline or whatever, and then you have all the 3 ratings. And then it finds out if it's a yes rating, then you add it to yes per tweet, if it's a no rating. So this is pretty self-explanatory here. So remember, I generated let's do import CSV. So I generated the ratings through a Python script. It wasn't an actual human who rated, so don't focus too much on the numbers, but in the sense, don't focus that it's going to be negative, there's not much agreement. Just focus on the process. And if you see, once this thing runs, proportion of all assignments to yes category is 50%. Proportion of all assignments to no is 50, close to 50. Overall extent is a 50% extent, and your kappa is just about 0.002. Well, it's not great agreement. So this is pretty much the process that people go through when they determine a data set in the first place. So I have a different table now. So we could take like the next 10 minutes, either through Jupyter Notebook or through your physical notebook. You can try and work out for this table, what will be the kappa value. And all of your clues are over here. So let's work this out and yeah. Sorry? No, it's not the concordance ratio. It's just the inter-rater reliability ratio. Yeah. So how reliable is your rating among people? So yeah, we could take about 10 minutes or so, or maybe less than that to just work through. And yeah, so I'll resume the next session in about 10 minutes. So for the exercise, you should be getting about 73% agreement, which according to this table is a substantial agreement. So in the interest of time, we'll move on to the next thing. So I think if you have trouble with that calculation on top, just feel free to modify the Python script and try to test out some sample data. So let's move on to, let me pin this mic properly. Let's move on to the next. One of the things that I wanted to chat about was the algorithm for sarcasm detection. And just I wanted to introduce to the maximum entropy algorithm. So before we go there, right, the problems of getting a statement to be sarcastic, like identifying for a machine to identify a statement to be sarcastic, right? This missing context. If someone says, I love being rich, right? Unless you know that the person is poor and is not that rich and just, just saying that statement, we don't know the context. So there's also missing expressions like this talk is, is going to keep me wide awake or something. I hope that's not this talk, but there's a human expression and all of those aspects that are missing. And the other thing is, machine to identify subtle contradiction, right? One of the examples is, I love the way this product is consistent with low expectations. Like somebody wrote a review in Amazon or something, and then they worded it this way. There's a subtle contradiction, right? I love is a very positive sentiment versus I love the way how this is consistent with low expectation is a subtle contradiction, the negative sentiment. So when you have a mix of these things, so basically what we're trying to do here is understand the nature of sarcasm, which in itself is very complex. And these are some of the things that in the machine learning space that they've identified, the subtle contradictions, sudden polarity changes, like a positive sentiment followed by a negative sentiment and stuff like that. And some of the business aspects of sarcasm detection is, of course, product reviews. You got to find out, like, average of so many reviews, how many people really liked your product for companies that do online retail. So for max entropy algorithm is a very traditional machine learning algorithm. Deep learning will do wonders, but this is just for you to go through this exercise. And in this notebook, I have a little bit of notes on what really max entropy is. So to put it in a very intuitive way, it starts with, I don't know anything about this data set assumption, right? I don't know nothing about this data set. That's the unknown assumption, which is maximum entropy, in the sense the entropy is high, which means the unknown is high. And then it starts trying to find a uniform distribution among, all the features that it has. Features, when I say features, I mean, how does all my sarcastic sentences have a question mark, like rhetorical questions, right? Like, does it have a question mark, or are my sarcastic sentences expressed in a certain word length? Can somebody build a really sarcastic sentence with a less number of words? Is that a feature? There are multiple features that you feed into this entropy algorithm, and it will try to find a uniform probability distribution among all these features. And it will try to see, oh, I saw more of these features, so I'm going to put more weight to this. And then it runs through this algorithm and then comes up with a certain prediction, right? So another intuitive example here, dogs and fried chicken, right? So we are looking at it, we know exactly which is a dog because we know there are certain features. Like there's eyes, we know that, okay, this looks like fur, but it's not. So it's our brain doing that really fast. Max entropy is something like that. Like you have this data set where nothing is known, and then you have this feature where you have two eyes. Does this picture have two eyes? No, it doesn't. Or maybe this does, and maybe this is a dog, and that kind of iterative scaling on and on again. And that's, if you look at the notes, it says like f of x is 1 if the feature is present, 0 otherwise. And then this is actually the max entropy formula. It's about assigning weights to features. And then finding a family of exponents which will satisfy this weight. To put it in another intuitive way, I have 10 documents and there is a 40% chance that the word professor is there in one document and other words are there 20, 20, 20, right? Then the max entropy algorithm will look at a document. Oh, it sees a word professor, it knows, okay, there's a 40% chance of the word professor across these documents. It sees another document, it doesn't find the word professor, then it says, okay, let me do uniform probability. There's a 25% chance across, there's a 25, 25, 25, 25 across these documents, right? That this could be sarcastic. And then it keeps going through this algorithm. That's the intuitive way to look at it. And you can definitely soak a bit on the exact math for it. So for this, one of the prerequisites to run this example is to install the Mega M library. So this is nothing but a library that is used by NLTK to run the Maxent classifier. So it goes through an algorithm called iterative scaling, which this library provides. And this is the procedure for it. And going through the code, we have this, imports. And I want to go through the features. So what are the features? That's pretty interesting actually. The features are how many words. So Kendall was talking about bag of words, right? So take a statement, bag of words. How many words are there in a statement? That's a feature. The length of a sarcastic statement. Do all sarcastic statements have longer lengths? Is that a trend? That's one of the features. Parts of speech. Tag the parts of speech in the sentence. Interjection. Interjection is words like or conversational words. How much of interjection words are there with a substantial increase in accuracy is observed with this algorithm? Do we have question mark in the text? Like if there's a question mark in the text, is there a rhetorical question? We just add it into, And then we run through this classifier and all we do is maxent classifier.train, just feed in the feature set in the format that it requires. And that's what it's trying to find. It's trying to find out behind the scenes, it will run your maximum entropy algorithm and it will give you certain statistics, accuracy and all of that. So if you look at this, if you run this, I have the Megam thing installed in my VM. So let me run it from the beginning. Oh, this particular VM doesn't have it installed. That's why it's saying I cannot find this environment. But I have it in my laptop. And finally, the accuracy that I get for this is about 60%, which is okay. It's not that great. And one of the reasons for it is, as I mentioned, you don't know context. You don't have a long memory of how, things evolved. If I say this talk is going to be so awesome, without, understanding your context across a period of time, it's really hard to find out whether it's sarcastic or not. So one of the things is having a memory towards these statements and context, right? Like if you want to do sarcasm detection, you got to have like a short-term memory of things. That's a good segue into the next talk, which is about LSTM, which is long short-term memory, which happens with neural networks, which do a much better job. With this, we can go back to trying to install in our respective VMs. We could install the Megam in our respective VMs. I hope you have your VM username and password, so we need to SSH into the VM and follow these steps. So once you install this, just go back to the notebook and just run this notebook, and it should give you the accuracy. And then the bunch of exercises here are like, here the maximum entropy algorithm is running with all the features. It's taken into account your parts of speech, your interjection, everything, right? So you can play around with it and say, I just want to use parts of speech alone. Go look at your data set and see, maybe, or I want to put my own feature. I want to give more weight to certain words. If there are, let us say there are words with countries in it, I want to give more weight to it. So you can just put all of those things and try out these exercises which are around. So I will give the rest of the time for people to just run this, So you can just try and run this by installing this library, and then we can play with it. And with that, like our next talk will be by David on LSTM. So I'll give the next 15 minutes or so to try this out. Do wave your hand if you need help. SSH into. So it's a very simple thing. Just SSH into your VM. If you're using Windows, use a tool like Pudi or any of that, and then just try running those Mega M installers.